Okay. Well, hello everybody. I think this is potentially the smallest number of people I've ever spoken to, including my boyfriend, but it's all good. So, my name's Melissa Gartside. Just a bit about me. I'm a materials engineer, so I did A-levels in maths, physics and chemistry, and that got me into a materials engineering degree at the University of Birmingham. Since then, I've mainly worked in internal combustion engines, from passenger cars and trucks through motorsport, hence the Formula One car at the bottom there, to where I work now, which is for Caterpillar. I'm based in the Europe Research and Development Centre on the Peterborough site. Perkins, you'd probably know it better as. So I work with teams that make diggers, loaders, and also all sorts of engines, from very small ones up to very big ones. Ones that provide power through generating sets, boat engines, train engines, to all the ones in the machines. So most people don't actually know what materials engineering is, so I'm going to tell you a little bit about that first. So we understand how materials are put together on the atomic scale, so the scale of atoms, and there are 10 million atoms in a millimetre, so that's very, very small scale. So we understand how the atoms stack up to make crystals. Now those crystals are arranged together in the microstructure, that's the microscale in the middle there. And how that's put together affects how those materials behave at the macro scale of that steel wire. So just as an example, I'm going to talk to you about polythene, which is probably a material you think you're very familiar with. So at the atomic level, we've got a backbone of a carbon chain with hydrogens on the side. But this version of polythene is called low density polythene, and it has these side chains. There we go, there's a side chain. And those stick out of the sides. So when you get up to the micro level, that stops the chains from packing together nicely. If you imagine putting pencils into a jar, they all fit together very snugly. But if you start using a biro that's got those nice little clips on the side so you can put them in your top pocket and look like a proper engineer, if you try and put those together, the clips get in the way and stop them from packing. So with low density polyethylene, as you've guessed from the low density bit, we end up with a very loose open structure, and the mechanical properties are not brilliant. Hence we use it for making things like carrier bags. It's good for those. If we take what's basically the same atomic structure, that carbon backbone with the hydrogen groups on the side, but this time we don't add the side branches, now we start looking at packing together more like the pencils. It actually looks a bit like a bundle of spaghetti that's been chucked into a pan, but the chains are much closer together, and in some places they all line up side by side and we get what are almost crystals. So that material is high density polythene. It's stronger, it's more rigid, and we can make items like the boat there, kayaks, washing up bowls, buckets, things like that. So I've been talking about how the atomic scale affects how materials behave. We've also got the micro scale and how we've processed it to make what we're making. So now we're talking about aluminium. If I take a bucket of aluminium and I pour it into a sand mould, I can end up with, the sand mould insulates it. It takes a long time to cool down, and we end up with very big metal crystals. So that means that the properties, they're not great. They're good, but they're not great. But what I can do is make a very convoluted shape, like the engine block there. That's full of passages for taking oil through the block, water through the block for cooling. And we can do that very cheaply because we can cast those in using sand in the mould, which we shake out afterwards, and it leaves voids. So that's a cheap way. And it's good enough for a sports car engine block. So not great properties, but good enough. Now if I take that same aluminium and I cast it into a very big ingot, and then I heat it up and I roll it, a bit like a pasta mill. So squash it down, keep squashing it down. That way I'm going to break up those big metal crystals and make small metal crystals, and that gives us much better mechanical properties. I then take the stuff I've rolled down, heat it up like this picture, and forge it into shape. So I've got a big mould and I squash it to a shape, and I can make struts like the ones on the left there. And if you can imagine, that is a much stronger material because it's got the fine grain size, the crystal size, and it's also able to flex. So it can cope with being something like a plane wing, because plane wings are quite heavy. When you're on the ground, the plane wing's like this. When you're up in the air, it gets pushed up, and it flaps around more than you might think during flight if you've ever sat near the wing and watched it. So you need a very strong structure that can flex. So we've managed to produce that difference by how we process the aluminium from the molten form to the solid. So we understand how materials behave because of their atomic and micro scales, and that also means we understand how they fail. So, failure analysis. Why is it important to know how something failed? Well, basically, we don't want this happening. It's not good. People die, which is not great. Loss of reputation, which isn't great. So when you have something like a plane crash, you're going to have a big investigation. You hear on the news that people are looking for the black box voice recorders. That's because they're trying to find out exactly what was happening with the plane before it failed, what it was doing, whether it was turning, which is going to put different stresses on it, to if it was going straight. But also there'll be teams of people trying to find every single piece of the debris from it. And materials engineers like me are going to be looking at how they've broken and trying to work out what stresses were on them at the time of the failure. Is there anything wrong with the material? In my world, because I work for an engine company, it's going to be a customer who's getting upset because they had an engine component like that connecting rod at the top, but now unfortunately it's in jigsaw puzzle form like the one at the bottom, and there's a big hole in the side of their engine and they're not very happy at all. And my bosses at Caterpillar want to know why it's failed. They want to know, was it a material problem? Was it a problem with the design? Or was it just the way the customer was abusing the engine? That kind of thing happens. So at that point, I'm going to be asking people, what was the machine doing that the engine was in when it failed? I'm going to be getting somebody to look at the data from the ECU, which is our version of the black box recorder. It's going to say what the engine was actually doing at the time of failure. I'm going to look at the surrounding components to see if there's any clues there. And I'll look at the fracture surfaces on that broken thing at the bottom and see if that gives me clues. So that's why I say we're crime scene investigators. The failure is the crime, and we're looking for the clues to find out who did it, why it happened. So I'm going to talk about a specific example now. So it's the 28th of January 1986, and a space shuttle called Challenger is sitting on the launch pad. Countdown gets to 0, the main engines fire, the solid rocket boosters fire, and the space shuttle starts ploughing its way up into the sky. 73 seconds later, it all goes horribly wrong. Unfortunately, all of the crew were killed. And so at this point, NASA are thinking, what happened? We need to investigate this. So they'll be listening to all of the communication they had with the crew. They'll be looking at the telemetry that was beamed down to the Space Centre. They'll also be looking at all of the videos they had, because they had video cameras looking at the shuttle. And what those saw was that there was a problem with the solid rocket boosters. The solid rocket boosters attach to the shuttle and give it a bit of extra oomph so that it can escape the atmosphere. So they're full of a solid rocket propellant that just burns and fires the gas out of the end. As you can see, they're made of a series of sections, and those sections all join together. And where you have two sections joining together, you have a rubber O-ring acting as a seal. In fact, you have two of them. And they discovered from watching videos of the launch that the problem was that those rubber O-rings had failed. Hot gas had come out of the side of the rocket booster and it had impinged onto the fuel tank. And we all know that when fuel gets hot, it explodes. And that's what happened. The fuel tank exploded. So I'm going to talk to you a bit about the properties of rubbers. So we all know what rubber behaves like at room temperature. We're familiar with items like rubber bands and bouncy balls. It's springy. You drop a bouncy ball, it bounces back up. You ping an elastic band, let go of it, it pings back to shape again. So they're not very stiff at all. So on our curve, they're here. The stiffness is low at room temperature. But if we drop the temperature, rubber doesn't behave the same at all. It becomes an awful lot stiffer. At a temperature called the glass transition temperature, stiffness shoots up and it behaves more like a glass than a rubber. So I've got some videos to show you how that behaviour happens. Okay, thank you. You arrived just in time. Okay, so if we watch the ball on the 25 degrees centigrade one, we'll see it's been dropped from the top, hits the bottom, and it bounces back up almost to where it started from. In fact, I think we're going to get a second bounce. The picture's really flickery because it's a high-speed camera. Yeah. So we've got that second bounce. So that's how rubbers behave at room temperature. The second video's at minus 70, which is the glass transition temperature. So you can watch the ball falling again. You see it hits the bottom. It doesn't really bounce at all. And that is the same ball. The only difference is the temperature. So, a bit more information about January the 28th, 1986. It was very cold overnight. There was a frost. This doesn't normally happen in Florida. This is really unusual. The temperature was -2 centigrade overnight, and it was the coldest they'd ever launched a shuttle at. And so what happened was these O-rings had stopped behaving like nice springy things and sealed and coped with the metal flexing. Instead, they went very stiff, they failed, and the disaster happened. So at this point, you're going to be starting to think, what can I do to fix this? And this is what NASA had to do. So you could pick a rubber that's got a lower glass transition temperature. That would prevent them failing. Or even, you could say, I'm not going to launch my shuttle until I know that the temperature of my rubber's above whatever the critical temperature is. What they actually did was they decided this joint was so safety critical they couldn't afford for it to fail ever again. So they changed the design to 3 O-rings, so you've got an extra safety back up there, and they also changed it so that the path of the joint, it was more difficult for the hot gases to get out. Okay, so I've talked about a plastics failure. This is a metal failure. So, the cheese grater tower in London, which is this one here. It's called that because it looks a little bit like a cheese grater. As you can see from the headline at the top from the Daily Telegraph, they've had bolt failures and it cost the steel company £6 million. So the steel company aren't going to be happy, they're going to have to be spending all of that money, but even worse, it's in the newspapers, so they're going to be losing reputation. That's really not good. That's why failure analysis is so important. So what happened? The whole of this building is held together with bolts that are about the length of my arm. You can see them here and up at the top. So these bolts, they had 3 failures. The first one hit the ground. They were very lucky it didn't hit a person or hit somebody's car and cause any damage. It very luckily didn't hit anybody. The second one, even luckier, it got caught in the structure. When the third one failed, you can see these tethers. They were put on after the first 2 failures. The third one was caught by the tether and prevented from ever hitting the ground. So, what went horribly wrong? One of those failed bolts will have been taken to somebody like me, who will have looked at it in a scanning electron microscope. So that's like the sort of light microscopes you've used at school, but it uses electrons, and that can get it up to very high magnifications. This photograph is at 1,000 times. And you can see that the fracture surface is really rocky looking. So it's failed along the boundaries between the metal crystals. This picture here shows you a slice through it. So you can see the failure is following those boundaries of the crystals. So this is actually quite an unusual failure for steel, and it gives us a massive clue to what went wrong. When we process steel, it absorbs hydrogen, and we can get rid of this by put the parts in an oven at about 200 centigrade, just like a pizza, bake them for a bit longer than a pizza, a few hours, and all of the hydrogen gets a chance to escape. Now, if we don't do that, the hydrogen just sits there in the structure, waiting. So we take our bolts, we take them out to site, and we do them up, and we apply a load to the bolts. At this point, the hydrogen wakes up and starts moving. And where does it move to? It moves to those crystal boundaries, and it makes them very weak and brittle. And you get enough hydrogen there, they start to crack. Now, if enough of those boundaries crack, then you haven't got very much metal holding the bolt together, holding the building together. And the building's going to sway in the wind, and that's going to put load on those bolts. And when that happens, they break. There's just not enough metal there to hold them anymore. So, I've explained to you a bit about what materials engineering is, who we are and what we do. And I've also explained to you why it's so important to know why things fail. So the next time this thing happens to you, you know who to call. And if you are interested in finding out what's gone wrong there and want to Google it yourselves, that's a Liberty ship. There was a metallurgical problem with that one as well, so it'll be interesting to find out. So, does anybody have any questions?
I do.
Yeah?
Dare I ask about the Twin Towers?
You can ask, yeah.
And the collapse of those?
Okay, that wasn't a materials problem.
Right.
That was a structural problem. It was the way they designed them. So they had a lift shaft up the middle, and the floors kind of spiralled round them. And the whole thing relied on that lift shaft structure and the outside walls being intact. And as soon as they got rid of a bit of the structure by knocking a plane into it, the whole lot just collapsed like a pack of cards. It relied on the structure for its strength. there was no safety backup, and they don't build towers like that anymore.
Right.
In fact, most of the time, I've shown you some examples where the materials went wrong, but generally, it's usually an issue with the design or the way people use things, not being how they were expected to, which is again a design fault.
Where?
Yes?
On your cheese grater problem, the bolt, was it the bolt that sheared or was it the nut holding the bolt?
I believe it was the bolt itself that failed. But I could be wrong.
That's the same building that had the reflective glass that was being pointed
I think
towards
that was the
side.
walkie-talkie building.
Oh, it's the walkie-talkie building.
Let's have a look. Oh no, the walkie-talkie's not in that picture. That's got really curvy glass, and it was just done such that all of the beams, a bit like a satellite dish, all pointed in one direction and started melting the plastic on somebody's car. Another design issue. Yeah, we all know Jag owners, they're not going to complain, are they?
So, anyone got any more questions? Well, thank you, Melissa. Thank you for that.
No problem at
Are you
all.
happy to take questions should anyone call you around the building?
Yep, always happy to talk about materials.
Brilliant. Thanks for that. Thank you for coming. Stick around for the next talk.
Thank you.
Next one's the invisible universe. Bear with us while we set up. Thanks. Thank you for that. Brilliant.